All right, as we complete our chapter on hydrocarbons, we want to take a look at a very strange little group known as the aromatics. And aromatics are carbon compounds or any hydrocarbon that contains what is called a benzene ring. And benzene has a very strange kind of arrangement. As you take a look at the picture of benzene, you might notice something a little bit strange with it. We've been looking at one set of rules for all of our hydrocarbons and all of our organic molecules so far, and that carbon must have 4 bonds. Analyze any one of these carbons, and you'll see that benzene seems to be violating this rule. Now, scientists and chemists really started looking for, all right, well, there has to be some double bonds in here. There had to be a few things going on, but so far all of our investigations into how benzene does what it does have only led to theories and no actual proof. Some of the things that we do notice about benzene is that all of the bond lengths are identical. What this would mean to us is that there's an even distribution of these 6 unaccounted for valence electrons that should be there, that are there, and bonding us all together. So there's been a couple of different ideas on how this works. When we take a first look at it, we might see something like this, in which we are looking at double and single bonds. But there's an issue. The more bonds that you put between any 2 atoms, the more closely they are bonded and they would be pulled together. So this wouldn't show us a nice uniform arrangement like the original picture. So then there was an idea, and this one is still hotly debated, hence the question mark, in which we look at resonance. And resonance would really just say that the electrons are flip-flopping back and forth, creating and breaking double and single bonds all over the place. And so this is all happening so fast we don't see or measure this. There is some evidence to suggest that resonance is a viable theory, but there's also some evidence to say that this doesn't really work. So, what we do currently accept, and the better of the 2 competing theories, is to say that these electrons are somehow delocalized. They don't really belong anywhere. This doesn't explain where they go, where they are. That will come in time. But what it does give us is this unique structure. If we ignore these 6 electrons and just say, hey, they're in here somewhere, then we get a uniform distribution of the other remaining electrons and a nice perfect bond length for all of benzene. So benzene is one of those little mysteries of the universe, and we're working with a theory or an idea that allows us to continue modeling it, but doesn't necessarily explain the where and the why of this smaller part as to where those 6 electrons are. So now we have this cyclic looking structure with a perfectly uniform arrangement of carbons, and this little circle in the center that we get is just there to represent that you have these 6 delocalized electrons. This one feature within it would differentiate it from something known as hexane, a 6-carbon cyclic alkane that would have a very same shape, but would have all of its electrons accounted for. So we identify benzene based upon this little 0 or ring within the hexagonal structure. Okay, and that's the one that we want to recognize. We may see this from time to time. If you see a hexagonal structure with 3 double bonds within it, it is safe to assume that that is also benzene in a resonance structure. All right, depending upon the resources that you see out there, some model this way, some model this way. We are going to endeavor on the quizzes and tests to show you this, but some of your homework material might still show you this. Okay, moving on. What are some of the properties of this unique benzene ring? Well, it does have a very strange molecular formula, C6H6. There's definitely not enough ways to get carbon to achieve all of its necessary bonds. We find it's also nonpolar, like any other hydrocarbon. What's really strange is it looks like there would be room for any other atoms to react in or be added into benzene because it does have such a deficient amount of hydrogens. It certainly looks unsaturated. You know, saturation was to have a full complement of bonds for every carbon. We're not seeing that. However, no matter how much we try, we find that it is unreactive with hydrogen. And this is just one of our examples. So what this would indicate to us is that it's behaving saturated. There's no double or triple bonds in that structure to exploit. It's not like the test for saturation. If I add bromine to a sample of aliphatics such as benzene, then what I would find is the color remains. It doesn't go anywhere. All of the carbon-carbon bonds in this are the same length. And something that we might remember from a previous course is that the bond length of two single-bonded carbons would be greater than two double-bonded carbons. They'd be pulled tighter together, and greater still than a triple-bonded carbon. So all the carbons are identical and bonded to only one hydrogen each. So we see all these violations for how we've been treating carbon so far. However, this guy is incredibly stable. It is unreactive, and like the alkanes, it behaves as if it is saturated. Okay, so these are a few of the reasons why the aromatics are a separate category because of the unique and odd behaviors of this benzene ring. Now, this is all material for, I would say, other chemistry courses. I would be aware of some of the properties of benzene, but as to being able to explain why it is the way it is, that's far beyond what we would be doing in Chemistry 30. So where we're going to go is just looking how to name it and deal with the molecules that possess a benzene ring. So there's all sorts of notes and helpful things on 3D1 to 3D3. I would certainly take a look at that. The rules have quite a few exceptions, and you guys are probably quite lucky that you're going to be doing this quiz from home because you'll be able to reference this whenever you come across an aromatic. Some of the rules that you'll be asked to memorize in future chem courses will be things like this. If there is a one alkyl group attached, okay, then we have a couple of things to look at. If the alkyl group is less than 4 carbons, or 4 carbons or less, depending upon some resources, then the benzene ring, that weird little 6-carbon structure, is going to be named as the root or parent. So we might get something like methylbenzene or ethylbenzene. If, however, the attached branch is 4 carbons or larger, 4 is kind of that weird spot, so we try not to show it to you, the benzene ring, or if the benzene ring is not attached to a terminal or end carbon, find the longest continuous chain, and the benzene ring is now treated as a branch and a prefix known as a phenyl group. You might recognize the YL suffix. So there is some variety. There are 2 names. This relates to the functionality of having this aromatic group as being fairly large and significant to the remaining carbons that are attached to it, or if it appears quite tiny compared to the other carbons that are there. One other really important one here, we're not going to split hairs, a benzene ring will also be considered a prefix or a phenyl branch if it is attached to an alkene or an alkyne. Okay, so we don't have double or triple bonds in our branches. They comprise a main root or main parent chain. If you have 2 or more alkyl groups attached, then the benzene ring is going to be numbered to give them the lowest possible numbering. We have a bit of an issue. For identical sets of numbers, we will then default to numbering it alphabetically. So you're in a ring structure with only 6 carbons. It is possible to come across a multiple arrangement in which you would get the same numbering right or left. But if they are different sized alkyl groups, then what we would do is number the lowest with the alphabetical priority. Rare thing. We haven't decided if we'll throw this in on the test, but we'll get back to it, and I'll show you a couple of examples. So we've now considered 4 classes of hydrocarbons as we look at this, and we have an order of reactivity. Alkynes, with the most space within them, are the most reactive, followed by alkenes. Alkanes and aromatics offer a similar reactivity. Okay, so that's a bunch of our theory around this. What we need to do is now just get back to our naming practice, and we will do the nomenclature of these aromatics on the next video.